Hey, Doug here again for Bug Amps, and we're going to be testing again today. Actually, the first video is going to just be explaining the circuit. So today we're not doing an old design of mine, we're actually doing a recent one I've just finished up. So I've got it right here. You might have seen a picture of it. I don't know if you follow our Facebook page, but this is the new thing here. And came out real nice, I feel like. Let's see if I can get a good shot of it here. Kind of see, put it in front of my face so face tracking doesn't ruin it. Yeah. Anyway, hopefully that'll give you a good idea what it is. But it's a push-pull amp, another push-pull amp. It's about the same power as the last one we tested, so it's about 8 watts per channel. It's very different though. It's hard for it to be more different than the previous amp. It uses output tubes. Very interesting little guys here. These are a regulator pass element tube. It's called a 6C19P or 6S19P. And they're little triodes. They're not really meant for audio duty. They're meant to be the pass element in a tube regulator. Maybe at some point I'll do a video on tube regulation. Then you will know more about what a pass element is. But until then, just believe me that they're not really meant for audio, but they're pretty interesting. There's other reasons why they're hard to use for audio, but they have some sort of positive attributes as well. One of which is they have an extremely low output impedance at the plate. But that also comes with some downsides, which is they have almost no gain. I think they have a gain of 2 to 3 optimistically, and obviously less than that in a real circuit. They also have a very high heater current, so each one of these little guys takes an amp to heat, and they're triodes, and so any ideas that you might have had about running ultralinear or pentode, those are out the window with these. You're running a triode stage. And so they have a dissipation of about 10 watts, I think. 10 watts each, something like that. That might be pushing it. I should probably look in the spec sheet before I quote that. But and since you're probably going to be running them in Class A or near Class A, maybe you won't be. Maybe you run them AB. I mean, this amp is slightly AB. It's mostly A, and then it goes into AB. In fact, maybe we'll test that in the second video. We might test exactly how many watts are Class A in this amp, and then how many watts are Class AB, because that would be interesting to know. Because probably with this amp, almost all of your listening is going to be Class A. And I meant it to be a completely Class A amp when I designed it, but then when I started looking at my power transformer options, there wasn't one that sat like right at a very nice Class A point for output voltage, and so I could have gone either way. I could have gone down in voltage, or I could have gone up in voltage, and so I went up a little bit, and that pushed me a little bit into AB at max dissipation. So that's neither here nor there, I guess, but I will explain that a little bit, because in a minute here I'm going to explain how I designed the circuit, because the design is actually fiddly with these, because remember, they have almost no gain, and you need to swing a lot of voltage at the plate of the output tube to get anywhere with a tube amplifier. And so that means that these things needed a ton of signal input at the grid. And so how did I achieve that? Also, they're a very low voltage tube. A couple hundred, 250 volts is probably the max you want to run with these. And so, yeah, that's that. The cool thing about them is that they're cheap. They made these by the box for radios in military equipment in Russia. They're cool tube. Like I said, they have a low output impedance. Why is low output impedance good? Well, if you remember, with our last amplifier was a pentode output, and remember the plate impedance of a pentode is in the tens of thousands of ohms. Well, the plate impedance of this triode is in the realm of 600 ohms. And so what that means is the impedance of the tube is reflected through the output transformer and determines the output impedance of the amplifier. And so with this tube, you don't need any feedback to lower the output impedance. You can run the output stage, no feedback at all, and the output impedance is still satisfactorily low. So, satisfyingly low? I'm forgetting my words. Anyway, let's move on to the explanation of the circuit. Alright, so here's the circuit, and just wanted to really quickly show you once again how I designed this circuit. I designed it on the breadboard. I designed it not in Spice, but actually sort of mocking this stuff up. And so here are my little test boards, you know, use that one. Here is 6H8C, right? A little dual triode. And here is the input tube. This is 6N1. 6H1N, 6H1N, 6N1. Anyway, I should know these things. It's a 6N1P is what it is, right? And I've also, it's not drawn on here, but I'll sort of draw it out in a minute here. I've got a little board that runs the negative bias supply. That's important on this one because it needs a huge negative bias supply, as you'll see. And also not written on here because it's not totally necessary is the DC heaters. I've run the signal tubes with DC power, and this is a little PCB that I've made for that. So we'll look inside the amp later on, maybe later this video, probably later next video. Alright, so what is happening here? So when I always design the output stage first. And so with this one, what I did is I just set up my output transformer. I already drew my load lines and everything. I probably should have gotten those, but just to display here. But I drew up my load lines and my operating point. My original operating point was actually closer to 200 volts on the plate, and that gave me a pure Class A operating point. But like I said, I got a different power transformer, and the high voltage went up a little bit. And I mean, obviously, I could have dropped that back down, you know, in the power supply, but then you burn off all of that power just as heat, and so it heats up your chassis, and you get less power, and you know, it's better to just use that voltage if you can. And so this came up a little bit, and my bias point obviously had to come down a little bit to preserve the dissipation of the tube. And so this will stray into AB when pushed hard. But I think you still are going to get 4 or 5 watts in Class A out of it before you stray into AB. So the first thing to notice here is, I mean, we picked our output transformer as 4K. These have a low plate impedance, and they can they're perfectly happy to drive a low impedance. And so 4K output transformer means 2K for each plate. That's what it's looking at in Class A, and in Class AB, then you're going to go down to 1K. And 1K is still twice-ish the plate impedance naturally of the triode, which is around 600 ohms. And so it's a good impedance to drive for this tube. Right. So you'll notice here that the grids, and it's capacitively coupled, the grids for this tube need negative 78 volts just to stay at around max dissipation. And so obviously you're going to need more than that if you want an adjustment range, or you can adjust the amp more into AB, right? And so I designed my bias supply to achieve 100 volts. So it'll achieve a negative 100 volts, but you can adjust it down to, what, negative 70 or something like that. And we're feeding that into the grid circuit with this 240K resistor. 240K is kind of high. I was trying to push that up as high as I could because I didn't want to pull down the voltage swing from the driver stage, right? And so I think that probably 200K might have been a better choice there, just because I think that these tubes maybe have a tendency, if they get gassy, to kind of run away on you. And so what happens then is that the ions in the gas pull the electrons off, causing the grid to go positive. And if you can't flow enough current through that resistor there from your negative bias supply, then the tube can run away. I haven't experienced that, and I've only been running this amp for a couple of weeks now, and everything is fine. So let's check back in a year or two after I've been running this amp day and night, you know, just to see what happens to it. Maybe that value will turn out to be perfectly fine. We'll see. Anyway. Higher values there, though, present less of an AC load for the driver stage. Now you see that our driver stage has a task ahead of it. because we've got negative 80 odd volts, right? And so that means to clip the stage, we need to swing in double that. So we're looking at about 160 volts peak to peak to be safe, right? And so 160 volts peak to peak, that is very difficult to achieve with a B plus of 230 volts. And so this is where the circuit gets a little bit tricky. Okay, so if you look here at the driver stage now that we've capacitively coupled, you'll notice that the supply voltage for that is 415 volts. And so how am I achieving that? I've got a single power transformer here. It's bridge rectified, and yet I'm getting output voltages of 230, 220 for the input stage, and 415. And so I will get into that when we look at the power supply in a moment. But just for now, know that we've got a supply voltage of 415 volts here. We've got 68K load resistors on our driver tubes right here. And then the plates are sitting at 225. And so we can swing up, we won't actually hit supply. We'll swing up and approach supply, right? So we can swing up quite a bit. And we can swing down, but basically, we won't actually hit, ground or whatever. We'll never get there. But, we're going to be able to swing down to probably 50 volts of ground, right? And so now we have a stage that's capable of swinging 160 volts peak to peak. So it can clip our output stage. And so having that extra voltage for the driver stage makes all the difference there. Now this is drawn a little bit funny, but it's probably familiar to you. This is a long-tailed pair. And in most schematics, they're sort of drawn, in my opinion, in a funny way. I don't like to draw them that way because I feel like it obfuscates the function of the long tail pair. But I think people are it's more recognizable. Whereas I've drawn this in a way that you would normally see like a split phase drawn out, sort of like top to bottom like this. But honestly, the long tail pair can be thought of as a split phase that just has another active element. And the other active element, all it actually does is cancel distortion. And so the nice thing about a long tail pair is that you can use the full supply voltage, not just a third of it or a half of it like you do with a split phase. So in an amplifier like this that needs a ton of drive for the output stage, long tail pair is going to be your natural choice. It's also a low distortion. It's a low distortion, high swing, and so the reason it's low distortion is because all of the nonlinearities of this triode should be canceled by the exact same equal and opposite nonlinearities of the other triode, right? And so they're swinging equal and opposite, and so the nonlinearities are equal and opposite, and so they're canceling. And so that is what's really nice about this. Another way to think about this is that all of the current, so this is a current source right here, it's a little LM334 precision current source. Perfect for this situation. It's right in the middle of its sort of happy operating zone, right? It's like I think it's a 40 volts max device, but it drops out like at a volt or something, 1.5 volts. And so it's sitting there happy at 9 volts, and the current is right in its sort of happy zone as well. It's a good chip for this, and so it presents a very, very high impedance, which means that it doesn't change its current, right? Voltage can swing across it, and the current remains the same. And so if you can swing voltage without swinging any current, that means your impedance is high, right? If you use Ohm's law. So your R will be very high if you're able to change your voltage without changing your current. Your R must be large. That's how that works. And so all of the change in current, so think about only the AC current, all of the change in current has to occur this way, right? Like this. So all of the change in current, all the AC current swings straight up and down through here. And so all of the change in current through this phase splitter has to go across these resistors. And so if those resistors are the same value, the voltage developed across them will be the same, but opposite, because this one you're taking it on the bottom of the resistor, and this one you're taking it at the top, so to speak, as as the current swings through. And so that's your phase split, right? And so the top one is driven by the grid, right, from the driver stage here. The bottom one is driven from the cathode. But it doesn't matter. These tubes, they amplify the difference in voltage between the grid and the cathode. So it doesn't matter if you drive the grid or the cathode. You get amplification either way, right? And so the tube doesn't know or care whether it's the cathode that's changing voltage or the grid. So this one down here gets driven from the grid, this one this one from the cathode, that from the grid right there. All the AC current is shared between the devices and therefore shared between the resistances. And so the voltage developed at the plates should be equal and opposite. And so it is. Great phase splitter. All right, so how are we getting signal there? I did this just experimentally. I put a tube in front, a 6N1P, and it was a little bit too much gain. And so the first thing I did was I ran loop feedback all the way around. And that brought the output impedance down to like 1 ohm. And it performed excellently. It was a really great performing circuit, but I was listening to it, and when I would remove the loop, to my ear, the sound would sweeten a little bit. Took a little bit of the edge off. You know, the frequency response was still good, the output impedance was still pretty low, but having that loop feedback around the transformer, and having just such a low output impedance, you know, it's not normal for tube amps. I think a lot of the reason people like the sound of a tube amp is that it doesn't have that solid state fraction of an ohm output impedance, and so ended up removing the loop. And so to drop a little bit of that gain there, I decided to linearize the input tube. So the input tube is just a regular single-ended triode resistively loaded stage, right? And those have distortion, because if you ever look at tube curves for, you know, just a regular old triode, you notice that the lines aren't perfectly evenly spaced. And so I decided, let's use that feedback to get rid of a little bit of that distortion at the input tube. And so that's what I did. I ran a little bit of plate feedback here. So that's what this is all about. You'll notice that this doesn't have a ground reference right here, and that's because it references ground through the feedback network right here. And so for my feedback values, I used fairly high values, a 500K and a 200K. And you'll notice here now, if you're running plate feedback like that, you have to load the feedback with a resistance, because otherwise the feedback will just be shorted by your source. Your source is going to be probably around 500 or 600 ohms, and so it's very easy for it to short any signal from a voltage divider of such high value, right? And so you have to load it. And so I used, these are just, you find these by experiment, you know, like I chose 22K, and that works really well. 20K would probably be fine, 50K would probably be fine, 10K is probably low, etc., etc. So we've dropped a little bit of our gain here with some feedback, right? This doesn't need a lot of swing, and so we're running this off of the lower voltage rail with another RC. I'll talk about that more in a minute. And you see we have plenty of input headroom. The cathode is at 1.2 volts, and this only needs 1.8 volts peak to peak to clip. And that's not even going to see that at the grid, because the feedback is going to reduce that at the grid, right? And so we're nowhere near clipping for a nice little input tube there, et cetera, et cetera. So we're using our coupling cap as double duty here. It's decoupling and lowering the voltage down here for the grid, and it's also, taking the low voltage side of that cap for the feedback network, because obviously this needs to be 0 volts, because that's our input, right? We don't want to fry anything down the upstream. Here we just a regular old resistor with a bypass capacitor on it. I should have mentioned that also with the output stage. I've got these little 10 ohm resistors to sense current. This is unnecessary, but I was trying to squeak out a little bit more lower output impedance here, and so I did bypass those current sense resistors with capacitance as well. And the reason why you do that is because if you just have a resistance on the cathode, there will be a voltage swing there, and it's a degenerative feedback. And any resistance there, you multiply that by the gain, which in this case is very low, right? So it would be 10 multiplied by 3 or whatever, so 30, and you add that to the plate impedance, and so that would be, change our output impedance of our tube from 600 to 600 and 30 or whatever. So not a big deal, but then that gets reflected through and it changes our output impedance. So maybe it would have been 4.5 or something instead of 4.2 or whatever. So it doesn't. It's just a little something I put in the circuit. It does little cheap capacitors to put in there to slightly lower the output impedance there. All right. So now let's talk about the power supply. All right, so let's talk about this power supply. Power supply is a little bit tricky, but it's pretty cool as well. So if you have a center tapped transformer, and this Antec unit I'm using actually has 2 windings there, 2 200 volt windings, and so it's 200, and then I'm just connecting them together in series, so the place they're connected just acts as a center tap, right? And then another 200 for a total of 400, right? And that's how I'm able to, after rectification and smoothing, able to get that 529 that I'm dropping to 415, right? So that's how that works. But the cool thing about a center tap transformer is usually you would leave the center tap floating, but you don't have to. The center tap will actually give you half supply. And so what I've done is just run the center tap over here, and the first thing I've done is I've run it through the middle of the first smoothing caps. Now why have I done that? The reason why is because usually you would need a set of balancing resistors if you're going to run caps in series like that, because the leakage current of caps, particularly electrolytics, are sometimes orders of magnitude different than each other. They're all small, but the amount of voltage dropped across each cap is proportional to its leakage current, right? Because Ohm's law, the resistance, if you're thinking of it like a resistor, the resistance is going to be determined by the current that's flowing for a given voltage. And so you're basically, if you're treating them like resistors, the one that flows more current is the smaller resistance and will drop different voltages accordingly. And so you don't want that, because you might have 500 volts and you might be thinking, I've got 800 volts to play with because I've got 2 400 volt caps in series here, but maybe one of them is dropping 500 volts and the other one is dropping 30. That's not very likely, but you want to sort of run a resistive divider network to sort of set those voltages apart from the leakage current of the caps. But in this case, you don't have to. You know that you've got half supply here at your center tap, so you just run half supply right through there, and so it holds those caps at that supply voltage there, at that half supply voltage there. So they're always dropping half, so they're not in any stress or anything like that. Also, you can take that half supply and run it through a little filter here, and you can have a dual voltage output. You got the cool thing about this is you can actually ground the center tap there, and you can have plus and minus if you want, if you're designing that way. Just like you can ground this one and have minus and more minus, so you can do it any way you like. But in this one, we are grounding the negative side of the bridge, and so we end up with 0, and then half, and then full voltage here. Right, so it's really convenient because we wanted low voltage and high current for our output stage, but we needed to swing a ton of voltage into the output stage to make it work, and in order to do that, you need to have a lot of supply voltage if you're doing a resistive amp. We could have put chokes here, and that would also work. If we wanted to run the whole thing at 230 volts, we could have run chokes, because chokes will allow you to swing above your supply voltage. And an amplifier that I'm just getting ready to build right now is going to actually take advantage of that. But for this, we're resistively loaded here, so we need, double, basically, the supply voltage, so we can swing a clean 160 volts peak to peak into our output stage. Right. So what are these filters? I explained these last time, I think, but they're just little capacitance multipliers. So these little N-channel enhancement mode MOSFETs make great little filters. They act just like pentodes. They're current sources at the drain, right? And so they basically ignore voltage fluctuation at the drain, provided that the gate source voltage is not doesn't have any noise in it. And so all you got to do is just put a nice big RC filter on the gate, and basically you've knocked out almost all of your ripple right there. Simple, easy, effective filtering. And I use this all the time. I've never had one of them stop working except for one time when we just basically shorted. We put a tube in wrong and shorted the high voltage through the heater, and that toasted one of these at one point. But otherwise, I've been putting these in amplifiers for what, 5 years now or something, and they I've never had one stop working on me. So they're really good little filters. And so here is our half supply filter here. I'm just doing the same exact sort of network there, and I'm also dropping it again though for the driver stage with a 1K and a 22. Right, just to filter a little bit more, isolate it a little bit from the current swing of the output stage. So that is what's going on there. You know, you got the main filters. You've got a big cap here because low voltage. So I put a 470 UF in there, so that's like big old chonker right there. And then this is just the driver stage, so they just get 22s and 22s, right? And you can trim the voltage on these, which I did a little bit here. You can trim them by putting another value to ground right there. I've got 2 million here, so it's not very big. I've got 750K to bring it down a little bit more because I had a little bit too much voltage there. And the smaller you make that, the more you trim the voltage down. But of course, that increases the drop across the device, and more voltage drop at the same current, obviously more heat. I sunk these to the top plate, and they seem fine. So that is the circuit explanation. I think I just need to explain now the simple network for creating the negative voltage, bias voltage. All right, so we need to develop 100 volts, negative 100 volts or so, and here's how we're going to do it. I don't know if you can see that. I'm using this little PCB. Obviously, you don't have to. You can just wire it up however you like. This is what it looks like. I've got these little 1-to-1 transformers. They're like a, I don't know, 3-watt something or other, but they're just 1-to-1, and so 120 in, 120 out. And then what we do is we obviously we're going to go through a diode, just a little 1,000-volt diode, whatever, that would cost you a penny, and then big cap, right, to ground. This goes ground as well. This is 120 in over here. And so suddenly we've got half-wave rectification there. Got big cap, you know, whatever size your budget, your space will allow. And then a resistor. And another cap, right? So we got nice filtering there. And then out over here we get nice filtered whatever. You know, it's going to be more than 120, but not that much. And then over here, we're going to have a resistor, right? Then a pot, 20 turn, something like that. This is going to be our, that's not very nice, Doug. This is going to be our negative voltage out right there. And then another resistor there. And so you just pick those. You know, you pick them so that your output voltage, you have a voltage here that's going to be, let's just say it's negative 100, something like that, or 100, 120 or something like that. And you just pick it so that these resistors are high enough value that they're not dissipating a ton of energy, but low enough value that they're not just going to not deliver any current at all, right? And you pick them so that the adjustment range of this is maybe negative 100 all the way down to negative 60 or something like that, all right? And then this goes off to, you make these, this is, you know, X4, right? And you just, these go right off to your little grid leak values at your output tubes, right? So simple as you please, nothing complicated there. All right, now in the next video, we're gonna test and see how I did. How did I do? I don't know. I haven't tested this amplifier before. I've only tested it when it was in its circuit phase on the bench, right? So this one is, it's gonna be interesting. I'm interested, who knows? Maybe I screwed something up. We're gonna find out in the next video.